for doing all the work. And I said can't give a computer talk because my wife is checking her email. So this is joint work with my co-conspirators, alphabetically. Me. One, and it's in two papers. One is CMP, if you look for us, 2009, and then Proceedings of the American Math Society, which I guess is 2010. And if you want copies, if you go to Dewey's website, which is .edu, you can always get copies for free. We don't charge. Okay. So first a review. A review of what? Since I didn't do anything, what am I reviewing? And it's a review of undergraduate calculus.
That's the exam.
Undergraduate math. It's also the result. So any undergraduate can do it. So in undergraduate math, usually in the U.S., third semester calculus, which I was teaching for the last 15 years. One of the reasons I'm not at Wisconsin anymore is I don't want to teach third semester calculus anymore.
So we practice for us now.
Yeah.
Partially, they're promoting you to advanced calculus.
Advanced calculus. So we have a surface, and we tell the students in third semester about surfaces, and if I use the usual notation, then we would write the surface as in the form z as a function of x and y. So you give me 2 points, x and y, and then we know how high we are, so we know a point on the surface, and then we tell students that we can actually find distances along the surface. And we use Pythagoras, very useful guy. So we use some Greek mathematics and write the Pythagoras. And then we know that the z, of course, is the partial of f with respect to x dx, partial of f with respect to y dy. And we plug that in, and we get the x squared plus the y squared plus the z squared, which is the partial of f with respect to x dx, plus the partial of f with respect to y dy. And we square that, and then we get this formula, okay, 1 plus the partial of f with respect to x squared dx squared, plus the cross product term, x dx dy, plus partial 1 plus the partial of f with respect to y squared, pardon my handwriting, dy squared. Okay, so that's how we do it. So given the surface, we can find the y element, the incremental formula for the length along the surface. So we know how to find the length along the surface, and we tell this to the students, and we give them exercises. Okay, well, you can immediately see that this is a metric, so if we want to use fancy notation, then we can write this as g11 dx squared plus 2g12 dxy plus g22 dy squared, and it would say, given the surface, we can find the metric. So in calculus, given the surface, okay, question mark, what's the metric? Okay, so the students are given that. We usually give them some function. It's just an exercise in checking if they know how to differentiate, take partial derivatives, and we do that stuff. Okay, so that's undergraduate. Now let's go to modern differential geometry. Okay, and what's minor differential geometry? One of the questions is the inverse problem, which is how we think in applied math. So what's the inverse problem? Which is, given the metric, what's the surface? Okay, so you can think about that. So if you wrote it down, which I'll just write the easy case, so you would say in this case that you have to solve the equations 1 plus the partial of f with respect to x squared equals g11, the partial of f with respect to x times the partial of f with respect to y equals g12, and 1 plus the partial of f with respect to y squared equals g22 at the most elementary level. And then you look at it and you say, okay, I took a course in PDE. Is it hyperbolic, elliptic, or parabolic? I went to class. I was very good. I learned that there were 3 kinds that always occur: hyperbolic, parabolic, elliptic. Which is it? And you see, none of the above. Okay, not so simple. So immediately, if you think about this, okay, it's a fully nonlinear system of PDEs, even at its most elementary level. So, what to do? Well, you can either be a fully nonlinear guy or a fully nonlinear lady and try to develop a theory of fully nonlinear PDEs, of which there's a nice industry going on. Or you can say, I don't want to do business in that with that crowd. Let's see if we can change it to a more tractable problem. So that's my goal. I don't like fully nonlinear problems, but I love to work this platform. So if I push this one, okay, I'll push the other one, where everything is. So the goal is, how can we get around this fully nonlinear elliptic story and still preserve something? So what's this next thing? Then we go back, and while that's working, you see, I'll work like an issue, I'll go right to left. So it's hard to write right to left and do math right to left. Okay, so what next then? Back to undergraduate mathematics. And the next thing you got, students, is things about curvature. That's usually first semester calculus, and we'll tell them about when we draw a curve. And I write it as radical f. And the question is, what's the curvature of that curve? And I'll do the evaluation right at that point. Okay? So at that point, which I'll call 0, f prime of 0 equals 0. So the curvature, f of is f double prime of 0. However, in calculus, class average would be too high if we actually told them that the second derivative is the curvature. So we inflict punishment on the students and put some stuff with the square root and f prime of 0, and it's either 2 hairs, I can never remember, or 3 hair, who knows? Okay, so, and of course that lowers class average because nobody can remember what that is. And what's the next thing you remember is it's completely irrelevant, because just pick the point and do the evaluation at 0. It doesn't make anything. The curve doesn't know who's 0 and who's not. So just put up a tangent line always where you want to evaluate the curvature. So the curvature is nothing more than the second derivative. Okay, so how do we do it for surfaces? Same idea. So let's take a surface. Something like, looks like that. And now I want some concept of curvature. So how did Gauss set it up? Well, what could it be? What's the generalization of the second derivative? Is the Hessian. So is nothing more, should be, that if this was z, x, y, and again, this is z equals f of x, y, what do? We just compute the Hessian at the point. So if I want to know some concept of curvature, I have to do something with the Hessian. So first compute the Hessian. Okay. So that's the Hessian. We evaluate it at the point. Okay, now it's convenient that where I drew it, this is the normal direction to the surface. So let's remember that's the normal to the surface. So if I actually had the generalization as it should be, if I had the surface any place, and I drew the line in 3 dimensions, and I drew the vector going to the surface, and I could construct the normal, that's how I have to do the computation. Because I just have to turn my head that way and look at the normal. So what should it really be? It should be the second derivative, the Hessian with respect to the radial vector, okay, the space vector going out to the point on the surface, dotted with the normal. xy, dotted with the normal. Okay, and that has a name, and this has a name, and you can use any letter you want, or pi or something. So that was given a name, and it's called the second fundamental form. Okay, so in Gauss's notation, he would have used something L, N, M, M, something like that, but roughly. So that would be the second fundamental form. And now we have a concept of curvature. Well, there's 2 concepts. Either you take the determinant, or you take the trace. Okay, if you take the determinant, you get this guy times this guy minus that guy times that guy. Okay, and you get that. And you get a concept of curvature, so I can take the determinant of this guy, pi, okay, and I get something, okay, and we call this guy the Gauss curvature. Okay. Now Gauss would have called this, usual notation is H11, one is H12, H12, so again you can put it in subscript form to make it tensor-like. So those are the concept, and we have a concept of curvature now. And that, now if you're doing other classes of problems, people are often interested in mean curvature, but in this subject, mean curvature plays very little role. So it's just a Gauss curvature that we're interested in. Okay, so I still haven't said anything about the problem, but you can see immediately what's going on. Okay, because for this guy, if I want equations for H1, H12, H12, it's nothing more than the Shell equivalence of cross partials. Now, if it was actually the normal, which just going straight up would truly be the cross partial. So on a flat surface, like a piece of paper, then this would just be the one vector, 0, 0, 1 going up like here, and this would be easy to identify, and we get equivalence of equality of cross partials. When I said equality of cross partials of x here, so that the x, whatever it is, y should be the, so this would be x, 2 x's, and I do a y, this should be equal to this one with another x. And this one, 2 x's, one, if I do an x here, no, a y here, right, this should be equal to this one with an x. But notice the normal is here. So I'm going to have derivatives of the normal when actually I try to equate cross partials. So there'll be an error term due to the fact that the normal isn't the constant. So no error term for a flat piece of paper, but for a curved surface we'll get normals. Okay, so we have equality. So I'll use some notation. Okay, so again, if I call this guy, if I do it this way, so I'll take make it more like, so I'll take the square root of the determinant of the metric, put it outside, divide, and then multiply. Okay, then I'll call this L, M, M, N. So nothing more than dividing and multiplying. Okay, so nothing very big there. So there's the Hessian. And now, when I perform this computation, I compute the cross partials. Okay? And I say equality. So R x x y has to be equal to R y of x x. Right? And so equality of cross partials. So you have equality of cross partials. So what do we get when we do equality of cross partials? Let me see. So it should be partial of L with respect to y minus the partial of M with respect to x. Okay. And then there'll be other terms because of the normal. Okay. If the normal was flat, no other terms. So there'll be some terms with an L, an M, and an N. And then a similar thing here. So this should have been, again, so this should have been, this is y, so I guess it should be m sub y. Hope I don't make a mistake. Minus n sub x. Okay. And again, something with L, M, and N. And it's not, so there'll be the Christoffel symbols here that have to come from the differentiation of the normal vector. So it'll be something. Okay. So far, so good. So what's it say? It says, if I know L, M, and N, the components of the second fundamental form, then I can find the surface. So that's the way to do the inverse problem. If you know L, M, and N, because they just second derivatives are, you can recover the surface. And L, M, and N are not independent because they have to satisfy these consistency condition. So this is a consistency condition. Or integrability condition. And they're called the Fadazzi equations. Sometimes called Maynard equations, but sometimes called Peterson equations. So why so many names for the same thing? And roughly, for the younger people, way back when, before there was internet, okay, before there was television, okay, back in the 1870s, okay, it's hard to believe people could still write there, but they just actually published papers, and it took time to communicate things. And this was an interesting topic at the time because shell theory was developing, and people were interested in surfaces. So surface theory was being developed by Fadazzi and Minardi all about the same time. Gauss was still, Riemann was finishing up with the end of his life. Gauss was maybe still alive, and they were developing these theories, so they were all developed roughly. So in the books you find different names for the same stuff. Okay, so then all we have to do is if we can find L, M, and N, we know the surface. So that's it. So then the question is, what's L, M, and N? Okay. So that would be nice to do. So make sure I have it right. This is x, y, so I differentiate this by respect to y. Yeah, I think it's right. Okay. So we want to find L, M, and N. And so what? Well, we look at it, and it's two equations in this simple setup, and three unknowns, L, M, and N. So one too many unknowns. So there better be a closure rule. So we have to close the system. And how do we close the system? Well, there's one piece of information we haven't used, which is that if I write this Gauss equation out, it'll be this determinant, which is L, M. If I Ln minus m squared, remember, and actually if I was in this notation, okay, it's equal to the Gauss curvature. It's the determinant. So this is what we call kappa. But this remarkable thing, and remarkable is the operative word here. So why is it remarkable? Because that's the name Gauss used for his theorem of Regium, remarkable theorem. And Gauss's remarkable theorem is that the Gauss curvature, I'm not sure Gauss called it the Gauss curvature, but the Gauss curvature, okay, can be determined only in terms of the metric. So the Gauss curvature, kappa, depends on G and its derivatives. So if you know the Gauss if you know the metric, which was the initial starting point, I said it's the inverse problem. Given the metric, find the surface. That's the thing we're given. So given the metric, find the surface. So given the metric, I know the Gauss curvature. So if I know the Gauss curvature, now I can solve for one of the three in terms of the other two, and I close the system. So I could solve for, I say m is a function of L and n, and solve the equation. Okay, so we can do that, but I'll do it in a slightly subtle form. Push the button again.
And the other way.
Oh, the other side. So let's do that. Let's leave the Kodatsu equation. So I work over here. Okay, now we get a new idea is brought into the business. Okay, if you look at that, okay, and stare at it for a few minutes, okay, you say then to yourself, let me see if I change the sign here, so I write it as partial of m with respect to x minus the partial of L with respect to y. Okay, that also equals stuff. We just multiply the first term by minus 1. And leave the second one, so that's also y, right? Okay. And then I want the MGS and the partial m with respect to x, that's right. Okay, minus the partial of m with respect to y. Equals stuff. And you stare at that. Of course, you see the M appears both sides, and the N and L switch, and you say, what does that remind me of? You say, well, I've seen that before. I just wrote a paper with Wei Chung and Dewa 5 minutes ago on transsonic flow. Sure looks familiar. And you say, well, let's see. What were the equations of steady state fluid mechanics in 2 dimensions? And if you stare at it, let's see, I think I want to do the L first, so let's write that as rho uv. That's it. M is x, right? So rho uv plus rho v squared plus p, and this would be rho u squared plus p plus rho uv. Of course, in steady-state fluid mechanics, we have 0 on the right-hand side. But if we look at it, I think I have it in the right order. So m should be minus rho uv. Right? Because that one has a minus. Right? That means L should be, this is the plus one, rho v squared plus p, which tells me n is rho u squared plus p. And now it looks like fluid mechanics, but of course, fluid mechanics, gas dynamics, p depends on rho, which you're given. That's an equation of state. Okay, so now I've been able to reformulate it Okay, now if I knew P, I could go back and have counted, this is number theory, 1, 2, 3 equations, right, in 3 variables, rho and u, v. Okay, that's my knowledge of number theory. So, so we have to think a way to close the system. Okay? So what do we know? Again, that we have the Gauss relationship, that it was the determinant, which is, what was it? It was Ln minus m squared was the Gauss curvature. Okay. Now we plug it in. So we take L, which is rho v squared plus P, times N, which is rho u squared plus P, and you subtract off m squared, which is rho u squared v squared, and you know that's the Gauss curvature. Okay, and if you multiply it out, the first thing you realize is you get rho u squared v squared, then you get P times rho, then you get a u squared and a v squared, cross product term, then you get a p squared, then minus rho u squared v squared equals kappa. And the first thing you realize when you're doing this computation is this, of course, perfect cancellation, which tells you this is a good idea. Anytime you get perfect cancellation, you know that this seems to be, because it's cleaning up the problem. If just to make the problem messier is not a good idea, but when the problem becomes simpler, then it seems it's a good idea. So now I have to close it, and the choice of P is up to you. So play around a little, and it doesn't mean this choice I'll give is any better than any other, but it's simple. So the simple choice of P that I'll work up here is P equals minus 1 over rho, and you'll see why. So this is just a simple choice. Okay, so if you make the simple choice of P, of course the reason is that get this term to clean out. And we'll call this, just like in fluid mechanics, the speed squared. So u squared plus v squared is the speed squared. And we get that P equals minus 1, so this becomes minus q squared. Very neatly. And now this one is p squared, which is 1 over rho squared, equals the 9 guy, which is the Gauss curvature, which means we could solve for rho as a function of q. Okay, so I could then write that the 1 over rho squared, of course, is kappa plus q squared, won't be the q squared to the other side, which means rho, okay, is kappa plus q squared to the minus 1/2, and the pressure, of course, is just a kappa plus q squared to the plus 1/2 with a minus sign. Okay, so we've related just by this artificial fluid interpretation, okay, the Gauss equation is a relationship between the density and the speed. But in fluid mechanics, that has a name. It's called the Bernoulli equation, which is usually the starting point of steady transonic or subsonic, steady gas dynamics. In 2D is based on a simple relation, the Bernoulli equation. Guicheng mentioned it in this talk. So you have a Bernoulli relation. So I thought, so one of my colleagues in Madison, when I started talking about this, the question was, so where's the fluid? Where's the fluid flow? And I said, no, there is no fluid. It's just imagination. It's just being able to identify. There's not anything in fluid mechanics, but it's a useful identification. So far, just translating one problem, which I wasn't familiar with, were Newton geometry. Okay, so for people who have some experience in gas dynamics and didn't have much experience in geometry, it was convenient to change the problem to geometry. And you notice, of course, we're not doing geometry, Taylor geometry, and complex spaces, whatever that is. Okay, this is a real number, so this has to be positive. So we have a restriction that kappa plus q squared better than greater than or equal to 0. Okay, so that's a relation. In particular, we're interested in the case where kappa is negative. Often. Now, if kappa can change sign, the problem, of course, is transonic. So we see the interpretation of surfaces like a torus, which changes as you go across the top from positive Gauss curvature to negative Gauss curvature, can be interpreted as steady transonic gas dynamics. So, okay, so this says, in particular, kappa is negative. Okay, call it gamma squared. Kappa equals minus gamma squared. This says q squared has to be greater than gamma squared, which means we're only interested in solving the problems, okay, if we're looking in the UV plane. Okay. So this is q equals gamma, and we'll have to work outside, okay, where the problem doesn't change type. Okay. Well, if you go across, then the problem will change type. So that's the outside. In fact, it's not a hard computation. I won't prove it. But if you think of what is p prime of rho? P prime of rho is the sound speed. So if we define p prime of rho to be the sound speed, okay, then the relationship p prime of rho, okay, so we know q squared is greater than c squared or less than c squared, means the flow is either supersonic or subsonic, and we know steady flow is either supersonic or subsonic exactly in this region, hence hyperbolic or elliptic. In fact, this is exactly the same. So out here, where q is greater, this is the supersonic, and this is the subsonic, and this is the parabolic change over the sonic line. So these curves in geometry have a meaning just to reflect the simple meaning in gas dynamics. Okay, so far it's just tautology, so what's the point?
Master, can I ask you something?
Yeah, sure.
What do you gain by being the problem from the fluid mechanics?
That's what we're
Reference and theory.
Okay, thank you. Okay, so let's get to the exactly the answer to Thomas's question. So let me erase here.
By hand?
Well, I don't want to lose the equations here. Primitive technology.
All control, right?
Yes. So let's answer Thomas's question because that's very important. Okay, so far just an identification of the two problems. Okay, so the question is, what do we gain by thinking of things this way? And okay, so here's the reason. First of all, we might want to find a way to generate approximate solutions. So how are you going to generate approximate solutions? So we'd like to generate approximate solutions parameterized by some parameter epsilon, and hope to pass to a limit. So we, as in all problems in PD, or most problems, how do you prove existence? You find some other problem that you know how to solve, and then you hope to pass to a limit, either by finite elements, finite differences, or some other way. Okay, so how are you going to do it? Well, if it was fluid mechanics, what would it be? This would be conservation of momentum. Linear momentum. So what terms are missing from fluid mechanics? So the terms that are missing from fluid mechanics would be, this would be V, so this would be partial V sub T here, and partial rho of U sub T. So those terms, if I embedded it into a dynamic gas dynamics, I'd have to put in the inertia terms. And if it was a viscous fluid, then I'd have to put in the viscosity, which would be something, okay, and this one would be something like Laplacian, say, rho V, and Laplacian rho U. Okay. So what do I learn immediately? I know what's the good way to make an approximate solution. There is no viscosity in geometry. So we've introduced a new, with all modesty, but my co-authors are here, so why be immodest, okay? We've introduced a new technique to geometry, which didn't occur. It's, so, at least in this, it's introduced this artificial viscosity. So artificial viscosity is introduced into a subject which has no viscosity. Okay. But now we have to understand the problem. So we erase these. So it tells us how to set the viscosity. Now, if I want to think of one of the two variables being time-like, since it's hyperbolic, then I shouldn't have the full Laplacian. I should only use the Laplacian in the variable that's space-like. So if x is time-like, and y is space-like, okay, then I don't want to use the full Laplacian, I'll just use the y derivatives.
Time-like and space-like, well, assume you have a metric beforehand.
Yeah, that's a given. So that's the initial, that's the inverse problem. Given the metric, find the surface.
Okay.
Okay. So now I have, so the first thing the fluid mechanics tells me a nice way to regularize. Okay. Now let's assume I've generated these approximate solutions. Okay, you can put the epsilons in for yourself. Okay. So let's say I can generate the approximate solutions and I get an estimate. Okay. Well, that turns out to be difficult, but let's say I could get an estimate. So let's say I could get an estimate. So assume an estimate for the moment. And LP would be good, T greater than 2, but let's work in L infinity because it's easier for this problem. Okay, so let's say I could get an estimate. So I could get, for all x's and all y's, and when I'm studying the problem, I can get an estimate that the u's and v's, because if I know u and v, I know rho, so the u's and v's are bounded in L infinity, which means the rho is bounded in L infinity. So what does that translate back? Let's go back to the original Kodazzi. So that says, now put in the epsilons. Okay. So now we put in the epsilons. Okay, so we put in the epsilons, and now what's the question? You'd like to know that you can, if L's, M's, and N's are all bounded in the form of the epsilon, what do you know? You know you can have a weak star convergence subsequence, so you can pass to the limit. Now, it looks like it's linear. Go ahead. So what's the limit of this guy? This guy will have a weak limit. Let's call it L bar. So each of those guys is bounded, so they each have a limit. So the L epsilons go to some L bar, the M epsilons go to some M bar, and the N epsilons go to some N bar. What could be easier? So you pass to the limit, and triviality. They have no choice but to do what you want. But of course, this one piece of information that has to be preserved, because you have to preserve Gauss's theorem of Regium, which in our case was the equation of state, but already getting Gauss's form. Remember, Gauss told us, well, I haven't spoken from Versailles recently, but anyways, okay, Gauss tells us that this thing is kappa. So you want to know that you can pass to the limit. So everything here at the PD is easy. The only thing that remains to be seen is can you pass to the limit here and get L bar, N bar, M bar squared equal to kappa. So can you preserve the weak limit of the Gauss equation, okay, is equal to the Gauss equation of the weak limits? And so that's the question. Okay, so now it gets a little subtle. When the nonlinear functions, here this quadratic guy, okay, when can you pass the weak limits of nonlinear functions? And the answer is almost never, as we know. Okay. Okay. So freaking problem. So when can you do it? And that's the other useful fact to answer Thomas's question of this formalism. So we need some way to do it. Okay, what's the useful way? Okay, is the theory of compensated compactness. Well, I won't go through the theory of compensated compactness. Guicheng has in his many articles, and on his webpage you can find many articles and discussion of compensated compactness. But let me put it just in this context, what the theory of compensated compactness tells us. In this context, it says you need to have that this guy plus this guy for the epsilon problem, okay, right-hand side, so the error term should be in a compact subset of H minus 1 low problem. Okay. So we need that the error, the right-hand sides, the errors you generated through the approximation problem are not too bad. You can't make big errors. And the big error, the size of the error is very well quantified, very precisely. Okay, that means we need very short error bounds on this guy. Now what's the theory of compensated compactness tell us? So if we wrote it over here, it's easier. So we have again that the right-hand side with the epsilon term from the viscosity should lie in a compact. So the right-hand side should have this compactness property. Now what's the theory of compensated compactness tell us? It says in the 2D setup, there is a nonlinear function which is weakly continuous, in this case weak star, in the sense of distributions, whatever, okay? But there's only one. Okay. Only one anybody knows. What's that one? The determinant. When I saw this, I'll tell you a little history of mathematics in the 21st century, which was Memorial Day weekend, and we're in Guicheng's office, and he had a copy of the book of Chin Han and Han from Shanghai, and we looking at the book, and I went to look at the book, and when I saw that the basic nonlinear function of differential geometry was the determinant, I was happy. Because that's the only nonlinear function I know how to do any business with, but that's the only one that occurs in differential geometry. Okay.
So it was on differential geometry, the book you looked at?
Yeah, it's their book.
Differential geometry.
No, I think it's called Isometric Embedding.
Okay.
I think it's published by the American Math Society, in fact. So what does it tell us? It says, if you put in the epsilon, the only one that anybody knows is weakly continuous is the determinant, but that's actually the one we wanted. So what does it say? It says if you can get the right-hand side in H minus 1 look compact, right, you're finished. And you've proven every embedding problem one. This is two-dimensional. You might have, okay, what happens in higher space dimension? Giant. Perfect. You can do anything you want. So all the problems of isometric embedding, the John Nash, and if you could get the LP estimate, you could do anything you want. But getting the LP estimate, which is no concentrations, so this says no oscillations can't hurt you, but of course the thing could concentrate, and balance could be uncontrolled. So there are no oscillation problems in differential geometry, which is rather interesting. Okay. If you want to think about it, okay, here's a surface with 0 Gauss curvature, because I ironed the shirt, which of course I don't know how to do, but if I knew how to iron the shirt, I could make it flat, which is 0 Gauss curvature. Okay, then you wear it, and you give the lecture, and it crinkles up, and it says, okay, if you're going to lose any problems, it's not because of the shirt oscillating, it's because it crinkles up too much. Okay, so in fact, that's all the very natural problems of isometric embedding is folding paper, origami, shirts, doing all 0 Gauss curvature. Okay, so now we need to get the estimates. So now we ask Thanos' question, okay, what good does this do you? Okay, well, if you think about it, this helps to have some experience. Okay, how did you get the Bernoulli relationship in gas dynamics? Where did it come from? If you pick up Baer's classic textbook on differential geometry, on transonic gas dynamics, first page Baer writes Bernoulli relation, and he writes down two equations. And he writes down u sub x, u sub y, minus v sub x equals 0. So he's interested in irrotational gas dynamics. So this is the rotation equation. And he writes down conservation of mass. Buchon has got this in his lecture. So this is mass conservation. So if you have irrotationality and mass conservation, okay. Then, with the use of the momentum equation, with the momentum equations, you get Bernoulli. And when at Brown, for Walter Strauss's birthday party, I was having breakfast with Kathleen, and I said, how come Baer's never did the derivation of the Bernoulli equation? And Kathleen wasn't too, it was early in the morning. Baer's was a pure mathematician. But the point is, where did the Bernoulli come from? It comes from exactly here. But then yourself, which maybe Baer's never did, I don't know. Okay, you see that it's reversible. So if you have Bernoulli and conservation of momentum, you have conservation of mass. Okay. That means for the epsilon problem, you'll have something like this, and there'll be a right-hand side. But the right-hand side here was in divergence form. But the right-hand side here will not be in divergence form. Here. You can work it out, and you have a right-hand side with an epsilon. And the Christoffel symbols too, but those don't play too much of a role at the moment. Okay. So what's the main thing? Okay. You'll have to generate estimates to do the H-1 log. Okay. So how do you generate estimates? You need an entropy. So the whole story of what is the entropy in geometry? Oh, entropy in geometry. Entropy in geometry. Okay. Okay. There's no second order thermodynamics for a body.
Now there is.
Well, and what is the entropy? The entropy is conservation of mass and the rotationality. So use one of these two. This one turns out to be that. So the mass conservation gives you an energy or entropy inequality that allows you to get the preferred estimate here just as you would normally do, say, for the heat equation. You'll get a gradient squared estimate, which is precisely what you need. The hard part, so what's the hardest part? Everything like this could translate into higher dimensions. What's the hard part? Is ironically, the hardest part is getting the L infinity estimate. And for that, you need a special metric, at least for us. So how do you do it? Well, you know what Joel has done, and you set invariant regions to get L infinity estimate. There's Riemann invariance. And in this picture, I'll just draw it, and then I'll be quiet. Looks something like this. First of all, it's not one of these small data results. Okay. There is a precise balance. So I'll first draw the two things. I'll draw two pictures. Okay. So what kind of metric, what's the physical problem if there was a geometrical problem that we know how to solve? So I assume the Korea has nuclear energy? Okay. So if you go to a nuclear power plant, you'll see the smokestack, and for some reason, it looks something like this. Okay? Which is a cathode of evolution. So it's a cathode. So you take, this is what I call X. So you have to do, this is Y, X, Y, Z. So the surface would be Z equals F of X, Y. So X is the time-like direction. So what you want to think of is giving initial data in X, because X is time-like, and so that says you're prescribing the cross-section. So for a catenoid, the prescribed cross-section is usually a circle. Now, what our problem would be, let's say you don't make it not a circle. Is it still a surface? And is it a smooth surface? And the answer is, that may not be smooth, but you can get the estimates. And how do you get the estimates? Well, you can draw some Riemann invariance roughly like this, and you'll get an invariant region. So if you started there with data here, this is UV data, which of course translates to data in the second fundamental form. Okay. Then you have the L infinity estimate. From the entropy inequality, you have the H minus 1 log, and then you have existence of solution. So it would say, you give me data here at minus x naught, some large negative number, as large as you want. Okay, you can solve the problem up to x equals 0, or give me data up here some plus x naught, and you can solve the problem down to 0. So it's not that the existence time is dependent on the data. It exists as long as you want. You give me so you give me some finite number, x naught or minus x naught, and you can solve the problems for as long as you want. It also says, I don't know why they build nuclear reactors that look like catenoids, because that's exactly the one that went develop shocks. So, which it makes you a little nervous about the nuclear reactor. So I would build something more stable, which won't have shocks. They precisely built it in the hyperbolic case. So that's a good place to stop. I went over a little bit. Thanks a lot.
Any questions?